So we left off last time, and I invited you to try to figure out how to do these things in Maple. And so what I'm going to do here in a second is I'm going to pause, and then I'm going to write down generally how you can do these things, and then you can figure it out. So if you're still working on it or you haven't tried them yet, I really do invite you to try. Play around with it, see what you can throw in as an option, an extra option in Maple. So I'm going to hit the pause button here, and then write the answers. And you can do the same. Okay, so here are the solutions to the puzzle. If you want a larger window, you can just change the XY scales. If you want to add slope field arrows that are green instead of red, you can just add the option color equals green. If you want thicker arrows, you can add the option thickness equals a number like 5. If you want to change the arrows to line segments, you can just write the option arrows equals line. And if you want to change your solution color so you get all kinds of different colors for each one of your solutions, however many you have, you can say line color equals, and then in square brackets, you can say color 1, color 2, color 3. So you can make each one of your solutions a different color if you wanted. Now, I'm going to switch over to Maple so you can see what this might look like. And I've got an example of each one of these so you can see. So here's an example of a whole bunch of changes made to my DE plot. I've got 4 solutions that particular solutions that I've added. You can see that I'm still using the same window size, but I could change that if I wanted to. The line colors, I've got 4 different colors: blue, black, red, and green. The thickness, actually, I had written it down, the thickness actually changes the thickness of the solution curve. So if I make that 8, you'll see what happens to the solution curves. It makes the solution curves thicker. It's the arrows large that makes the arrows larger. So if I do thin, make it a little bit easier to see what's going on. And then arrow size, if I change that, you can see what happens. Changes the length, the relative length of those arrows. So if you don't say arrow size, it'll just use the default, right? Whatever the default happens to be. I think it's just 1. And so you can see a pretty standard looking DE plot there. And then of course, last but not least, I can change the color of the arrows if you don't like the standard red. So there's lots that we can do. All of these, everything pretty much after the y equals -5 to 5, all of these, oops, let's see if I can do it. All of these guys here, up to there, those are all what I call options, right? And so all of these, you don't have to have them on there. If I delete that and just do this, Maple says, no problem. That's your standard, that's your default. Red, slope field lines, slope field arrows, and this kind of pukey orange, or not orange, yellowish sort of colored curve. I never like that. I always like to change the color. So I'd go with something a little bit more kind of standard like this. So you can change all of these things. You can do that to make it easier to see. You can change those settings as you see fit. The other thing that I'll kind of draw your attention to is that we can also add a title to the graph. And titles are often really nice, especially if you're trying to have somebody else understand what's going on. So I can say this is the DE, or this is the slope field plot for dy dx equals, what is this, x minus y, I think. Something like that. Oh, what did I do? Oh, I forgot my quote at the end of it. So that's what I want the title to be, and that's what Maple puts at the top as a title, right? It's nothing fancy, but it's a way of kind of identifying. The other nice thing about this is, of course, I can click on the graph, and I can kind of save this. I can export this if I want to as a picture. If I wanted to import it as a JPEG into another document or something, I could do that. You can also change the relative size by grabbing the corners of this thing and kind of dragging it around. So you can change the size. Notice that the font of the title doesn't change. So that's pretty standard procedure. So we'll switch back over and take a look at some special cases in the notes here. And so here we are in the notes. This is page 24. and we're taking a look at some special cases. And the first one is, what happens if the derivative, dy dt in this case, is a function of only the independent variable? And again, I'm getting some, sorry about that, I'm getting some glare from the light in this room, but dy dt is only a function of the dependent variable, or independent variable. And so if I do a dE plot, you can see something that looks kind of familiar. Now, we know how to solve this differential equation, right? This would have been a differential equation that we would have solved in Calc 1, right? This is like dy dx equals x. We know how to solve that. We know that every solution to this is going to be of the family 1/2 t squared plus a constant. Now, we know this because that's a pretty standard take the integral of both sides with respect to t. And what you find out is the graph, the slope field, looks exactly like you'd expect it to. You wind up with every curve that's on here is a parabola of the form 1/2 t squared, but they're all just shifted vertically, right? So these are all the possible solution curves. And on the next graph below, if we add some solution curves, we're adding these guys right here, which are the initial conditions. And these are 4 particular solutions. And on this graph, they'd be solution curves, right? And so you can see those initial values, y of 0 equals -4, that's this guy down here. Y of 0 equals -1, that's this one. Y of 0 equals 2, that's this one. And y of 0 equals 3, that's this guy right here. So there's 4 particular solution curves associated with their initial conditions. And so all of these, they're the same shape as each other. They're just shifted vertically. So all have the same shape, but shifted vertically. And this is important because what we're seeing is when you have a differential equation that is only in terms of the independent variable, then what it's saying is the slope only depends on where you're at in this direction, right? So if you're at -4 or at -2 or at 2 or 4 or 0 or anywhere in between, if you are anywhere on that vertical line, every place has the same slope. The slope only depends on where you're at horizontally. There's no vertical component to it. And this is what it looks like when we have that happens. And so what we're seeing here really is just that plus c from the integration is the same thing as a vertical shift. Of any solution. Right? And that's what we mean by a family of curves. There's literally infinitely many solutions. They're all just varying by whatever constant is at the end. And that gets us through this page. And so we'll stop here. The next couple of pages are kind of a quick look at how Maple gets interpreted. So we'll stop here.